In this video, we'll take a look at section 11.2 Goodness of Fit tests. The first item we need to look at is chapter 11. We're going to be analyzing categorical data instead of continuous or discrete data. In section 11.3, we'll be looking at contingency tables, which you've worked with before in probability, and that's a two-way table that describes counts of two characteristics. So this is an example of a contingency table, and we'll actually look at this table and solve that problem in section 11.3. The distribution that we use for categorical data is something called the chi-squared distribution instead of normal or student's t. And this is what we'll use for section 11.2 and 11.3. Properties of the chi-squared distribution are listed below. These are from section 7.4. The chi-squared distribution is not symmetric. It's not like the normal and student's t. As the number of degrees of freedom increases, the distribution becomes more symmetric. The values of chi-squared can be 0 or positive, but they cannot be negative. And the chi-squared distribution is different for each number of degrees of freedom. As the number of degrees of freedom increases, the distribution approaches a normal distribution. So all of the tests that we will be doing in chapter 11 result in a one-tailed test. The chi-squared is always going to be 0 or positive. All right, the first item for our goodness of fit, our objective is to conduct a goodness of fit test, to conduct a hypothesis test to determine whether a single row or column of frequency counts agrees with some specific distribution, such as uniform or normal. So our first example, a random sample of 1,005 subjects were asked to identify the day of the week that is best for quality family time. Consider the claim that the days of the week are selected with a uniform distribution so that all the days have the same chance of being selected. So the table that we have, these are the observed values. These are the actual responses. Our notation O represents observed frequency. E represents what we would expect, found by assuming whatever distribution. In this case, it'll be uniform. K represents the number of different categories or cells, and N represents the total number of trials or observed sample values. So O, the observed frequencies, are listed in the table. The expected frequencies are those we would get if the claim is true, that all the days have the same chance of being selected. If that were the case, then 1,005 subjects divided by 7 is equal to 143.6. That's a uniform distribution, and that would be the expected value for each day of the week. E is equal to N divided by K. The requirements for a goodness of fit test are that the data have been randomly selected. The sample data consist of frequency counts for each of the different categories, and we do have that. And for each category, the expected frequency is at least 5. We calculated that above. We got 143.6, so we do meet the 3 requirements. Null and alternative hypothesis in this case. The null is that the frequency counts agree with the claimed distribution. So for us, that would be the counts for the days of the week are the same or uniform. The alternative hypothesis is frequency counts do not agree with the claimed distribution. So for this, the counts of the days of the week are not the same. The test statistic, to find that chi-squared, we would take the sum of our observed minus expected squared divided by expected for each item in the table. So what I've got, the table here, we have our days of the week, our observed values, our expected values, and then the observed minus expected squared divided by E is in the row across the bottom. If you take the sum of all of those, we get a chi-squared statistic of 1,934.6. Now the TI-84 calculators will run this test. You don't have to find the observed minus expected by hand. So on the calculator, the TI calculator, 84, what we do, well, let me finish this out. These can be done using list operations on the TI-83, and I'll show you how to do that. And then the p-value is probability of getting a chi-squared of 1934.6 or greater. So using the TI-83 calculator, we would select chi-squared distribution and find the area associated with a chi-squared value of 1934.6. So let me show you the TI-83 how this works. So what we would have to do with the 83 is we would have to go to Stat, Edit, put the expected or the observed values in list 1, 523, 20, 9, 19, 11, 41, and 382. So those are observed values. Let's see, do I have them all in there? 523. Oh, I have these. Okay, so let's go back up and edit that. That would actually be 20, 9, let's see, let's insert a 9 so I don't have to retype all that again. So now let's check. 523, 20, 9, 19, 11, 41, 382. Okay. Then in list 2 we would have put the expected counts, which is 143.6 for each. So we get all of those typed in. Almost there. There we go. We've got our 7 values. Then in list 3, instead of hand calculating each of these, taking observed minus expected, squaring the result, and then dividing by this, you can go up to the top of L3 and type in a formula. So what we want, take our parenthesis, we want everything in list 1, because those are observed values, hit second and then the number 1, minus the expected values are in list 2, second, number 2, close our parentheses, we want to square that value, and then divide it by all of our expected counts, which are in list 2. Hit enter, and all those calculations will be done and in list 3. So there's our 1002.4, etc. Okay, so you don't have to actually add these all up and find these by hand. Then if we want to take the sum of this list, we don't have to add the items by hand here. If you go back to, let's quit and get out of here. Inside list, let's see, take a look at right above the stat key, it says list. Hit second stat. There's something called operations, something called math. This right here, pick option number 5, the sum. And what we want is the sum of everything in list 3. So you can tell your calculator sum up list 3. And there's our chi-squared value of 1934.59. So you can use the lists to make the arithmetic a little easier. Then to get the chi-squared statistic, there's a chi-squared CDF. We want the cumulative area from 1934 to 1E99 to infinity with degrees of freedom of 6. So we go to second, distributions. Notice it's below the normal and the t. There's a chi-squared CDF as option number 7. And we're going to type in the chi-square statistic 1934, comma, to infinity, comma, and degrees of freedom is 6. Hit enter, and this will give you the p-value. So that means the probability, that's a very low p-value and a very huge chi-squared statistic. So what does that mean? Okay, that means that we reject the null hypothesis and conclude that the counts for the days of the week are not uniform. And we can see that from the distribution. I do want to let you know that the 84, if you have a TI-84, it has a goodness of fit test already built in. You do not have to use the list operations. The directions are here. There's stat, tests, chi-squared goodness of fit test. You still put observed values in list 1, expected values in list 2, and then degrees of freedom of 6. Hit calculate, and it will give you the chi-squared statistic and the p-value, and then the CNTRB, the values we calculated above in the table. If you press the store key and then second 3, it'll store those values in list 3 so you can see them. All right, let's try another example. This is Binford's law. And according to Binford's law, a variety of different data sets includes numbers with leading first digits that follow the distribution shown in the first 2 rows of table 11.4. The bottom row lists the frequencies of leading digits of the populations of all 120 counties from New York and California combined. Test the claim that those 120 counties have populations with leading digits that follow Binford's law. So now it's not a uniform distribution. They're telling us in Binford's law that the leading digit happens 30.1% of the time, leading digit of 2 happens 17.6% of the time, etc. So when we're constructing our table, first of all, requirement check. The sample is not random, but we treat them as random for the purpose of determining if they're typical. And then the sample data do contain frequency counts, and there's an expected frequency of at least 5 for each. So the null hypothesis is P1 is 0.301, P2 is 0.176, P3, that just lists what we think the proportions are for Binford's law. And then alternative is at least one of the proportions is not equal to the given claimed value. So what this looks like, calculations by hand, we've got observed values here in this category. There are a total of 120 counties. To get expected values, we take 120 times each of the percentages in Binford's law, and we end up with these expected counts. And on your calculator, list 1 would be your observed, list 2 would be your expected, and then if you have the 84, you can run the test directly from here. If you have the TI-83, it does not have the test in there, so you'll have to use list 3 to write your formula of observed minus expected squared over expected, and then use the list column sum of list 3 to get that chi-squared statistic. Okay, either way, then you would have to find your p-value by using the chi-squared CDF in the calculator. So either way you go, the p-value ends up being a 0.652 and our chi-squared of 5.96. Notice that that is not a small p-value, it's large. So the conclusion is, since the p-value is greater than significance level, there's not sufficient evidence to reject the claim that the 120 counties have populations with leading digits that fit the distribution given by Binford's law.